right, we are going to go ahead and begin the next talk. So up next we have Eric Escobar from SecureWorks talking about practical wireless hacking using an SDR. And Eric is one of the most passionate guys I know when it comes to wireless security. Like last, we were talking about a little side project, and I think you were in the process of trying to get like a 12-foot satellite dish to put in your backyard. So if you ever want to know anything wireless, Eric is the guy to do it. He's got all sorts of crazy, wacky adventures relating to hacking wireless. And so after the talk, I'd love for everybody to get the chance to just hang out and ask questions. One of the questions I highly recommend is about that time in the airport, but I will say no more, and I will let Eric start with that. Thanks for speaking, man.
Hey everybody, my name is Eric Escobar. So a little bit about me. I'm a pen tester here at SecureWorks. I do a lot of our wireless stuff here at SecureWorks. And one of the things just as far as wireless hacking goes is that I feel like when I start talking to somebody about it, they're like, oh my gosh, but the hardware and the software and the knowledge that you need is just, over my head. I'd rather go do something else. And hopefully this is where my talk is going to, give you start a foothold of what you can do, how you can compare things, and making it not as hard as anybody thinks that it is. So first of all, we're going to talk about SDR. If you're not familiar with what that means, it's software defined radio. And really the perk of this is that everything is done in software on a hardware device. And what that means is if you're driving in a car and you have to manually adjust the dial of your radio, that would not be a software defined radio. And what that means is basically you're having to tune to the specific station that you want to listen to directly. With SDR, all of this is done in software. And so what that means is that you can get a wide range of different settings and configurations that before you would probably have needed some specific hardware. An example of that would be, if you look at Wi-Fi. Wi-Fi, you can get an ESP8266, just tiny little chip that costs about $1 off eBay. But if you wanted to emulate that entire stack in software, it'd probably be like a $2,000. Sorry, it looked like I got muted. So where was I? Let me go back a couple slides. So if you had like a standard little Wi-Fi adapter that might cost you $1, in software it makes it a lot harder. So there's trade-offs going back and forth. And hopefully this is what I'm going to look at. And so you can see the images here. It's a hack RF and a yardstick one. I'll talk a little bit more about these going forward. So when you look at a software-defined radio, they come in all different shapes and sizes, and you might look at this and say, okay, let's compare two side by side. Now, it's kind of hard to see in this image. On the right-hand side, you have a USRP, an Edis B210, and it's just the board by itself. And if you squint a little bit, you see the price is just roughly, $1,500, which is a huge price tag. On the other hand, you can look at something on the left, like a Hack RF1, and it runs about $300, and it even comes with an antenna and USB port and all the other stuff that you'll need. And when you compare the feature sets side by side, this is the first part that I see a lot of people kind of get stuck at as far. This is the part that I see a lot of people get stuck as far as trying to compare the specs and trying to figure out what radio is going to be best for me. And so we'll kind of go through what these different specifications mean. So if you see, operating frequency, duplex, bandwidth, samples per second, these are all things that, that may not mean a lot to some of you. So first of all, we'll talk about duplexity. If you see like half duplex, which if you go back to the Hack RF1, it's a half duplex transceiver. That means that you can only transmit or receive at one point in time. So it's kind of like a walkie-talkie. That's the best, kind of example of you can only talk at one point in time, or you can only receive at one point in time. Which for some applications, it might be totally fine. If you're trying to hack, say if you're trying to do a replay attack, having something that's half duplex might be all that you need. On the other hand, full duplex means that you can transmit and receive at the same time. So an example of that would be a phone conversation. You can talk and listen at the same time. And that'd be kind of similar to like uplink and downlink. So satellites, for example, they have, uplink frequency and a downlink frequency, and that's so that you can have two-way communication at the same time. So just when you see duplexity, you'll see that half. You'll see that full duplex is that you can transmit and receive at the same time. With full duplex, you also see something like something called MIMO, MIMO, multi in, multi out, and basically you can take multiple, you can send and receive on multiple different channels and multiple different bands, basically. All right, next is samples per second. This is probably one of the easiest for many people to understand, just because when you think of audio sample rate, or if you think of video sample rate, you can get a good idea how it's working. And this is typically measured in millions of samples per second. So the higher cost $1,500, or yeah, $1,500 software defined radio, it can record a lot more samples per second than can a hack RF. And why that matters is, if you see down below, if you have too few samples, you're going to miss data as it comes in. And if you miss data, that means you're probably not going to get a reliable signal, and it'll just look like static, or only a partial signal coming in. If you have too much, on the other hand, you'll be able to see your entire signal come in, but you're going to be capturing a huge file size. And a good example of why samples per second actually matters is, if you try to use the hack RF can't do enough samples per second. Like, it can't receive and record enough samples per second to snag, let's say, Wi-Fi. And so in that circumstance, you'd see too few, and so you wouldn't get a reliable signal from just your typical run-of-the-mill home Wi-Fi connection. You would need, something along the lines of the Edis, the $1,500 radio, in order to receive the full amount of signal coming in. But you're going to increase your file size. So really, what you want to aim for is something in your Goldilocks zone, to where you can receive enough samples, to be able to accurately see what the signal is that's coming in, but not so many that you're going to completely, freeze up your entire hard drive, or, just create massive, massive files that your computer's gonna have to try and chunk through. The next part about this is frequency range. So this is really just, how high or how low of a frequency can your radio see. So there are obviously tons of different frequency ranges for tons of different wireless applications, and really all frequency is hertz, and that's 1 cycle per second. And so if you hear, oh, this frequency is 2.4 gigahertz, which is what Wi-Fi is typically on. Gigahertz is billion samples per second, or billion hertz per second. And so when you hear 2.4, that's 2.4 billion cycles per second that are actually happening, as far as Wi-Fi is concerned. And then when you hear a lower frequency, that is basically just decreasing that. So if you see something like your garage door opener probably uses something along the lines of like 400 megahertz, or million, cycles per second. Let's see, let's keep going. And so when you look at typical ranges, I just swipe this off the internet, and you can kind of see these are what typical applications use. So you can see that, anything radio astronomy, satellite communication is going to be much higher frequency radio traffic. And then you're going to start getting into, UHF and VHF. That's kind of like what your cell phone uses. And that's in, the 300 megahertz range. And then as you start going down the spectrum, you get into the ham radio bands, shortwave radios. You get in your AM, stations that your car can receive. And then as you get into the very, very low, frequency ranges, that's like what maritime uses, or, military uses for really long distance communication. And one thing that I didn't put in the slides is that typically a rule of thumb is, the higher the frequency, the shorter the distance that it can travel. The lower the frequency, the much farther distance that it can travel. But the trade-off is that with high frequency communication, you can get a lot more data. Whereas with low frequency communication, you may not get a lot of data through, but it can go a long ways. So just looking at, I basically threw up on here all the different specifications that you can see in a bunch of different software-defined radios that are on the market. You can get a $20 TV tuner that's just USB that plugs in and has a huge frequency range. You can see it has 24 megahertz, a million, 24 megahertz, cycles per second, all the way up to 1800. And a pretty good sample rate of 3 million samples per second, all for $20. But you'll notice the TV tuner can only receive. So if you just want to decode signals, this might be something to get started with for just $20 on Amazon. If you want to start transmitting signals, the price is going to go up about what, 5 times. And so the yardstick is another great thing to get started with, another great software defined radio to get started with. But you can see that it's limited in the frequencies that it covers. Next, you'll see the hack RF. The hack RF is probably the sweet spot about where you can get started. And with it, you can receive and transmit. You can get a pretty good sample set. However, it is only half duplex. That means you can't transmit and receive at the same time. And you see the price of it, right? It's $320. It's a lot of money, but if this is something you want to get started with, it's a great point because it's an investment that you can then continue to use, and it'll take you through pretty much all of your off the shelf commercial electronics that aren't Wi-Fi. Next, you can keep going up and you see the Blade RF, and then the USRP B205, and then past that goes the B210, which is what I showed at the beginning. And you can basically just see that the more price goes up, you'll get full duplexity, meaning that you can, again, send and receive at the same time, higher samples per second, so, wider bandwidth as far as like what you can, receive on, and the price goes up. So just when you're trying to compare something, you have a project, this is just a good go-to of just, a gut feeling of like, do I really need a $1,000 radio? And typically you probably don't. You might be able to get away with just a $100 yardstick or, a $300 hack RF. So taking a look now back at what we had at our original slide, if you look at the feature set of the USRP, the B210, it's full duplex and it has 2 transmit, 2 receives. You get a full bandwidth. You can receive up to 56 megahertz of bandwidth all at the same time, 61 million samples per second. And then there's other features of what other software it can run on. And then you compare that to the hack RF. You see, okay, well, it has a similar range to that of the B210, but it can only do about half of the bandwidth that it can receive at a single point in time. It can do about a third of the samples per second. And so these are just things kind of to keep in mind when you're comparing the two of them, that you may not need the $1,500 radio. It may not always mean higher cost is going to give you better results. And so hopefully you can use this going forward when you're trying to spec out for a project that you're going to do of what exactly you need and not get bogged down in cost of hardware. All right, let's move on. So let's take a look at how practically we can use this and what practically we can do. A lot of devices, especially those sold in the United States, include what's called an FCC ID. This ID is basically what manufacturers need to get approval of from the FCC in order to be able to sell it within the United States. And the idea behind this is the FCC doesn't want to import a bunch of electronics that cause a bunch of interference, cause a bunch of noise, that's going to disrupt stuff in your house, right? So you don't want to buy some piece of junk off Amazon that you plug it in and all of a sudden now none of your Wi-Fi works. And so because of this, every device has an FCC ID. And what's great is that it's all public for the most part. And so if you look at the back of a device, you take your wireless mouse, you go look at the back of your, if you dig into your settings of your phone, if you go look at pretty much anything that's wireless, you'll see this FCC ID associated with it. And that provides a wealth of information. I mean, I got this tip a long time ago from watching one of Sammy Kamkar's talk. He uses a website called fcc.io, but there's a bunch of them out there. Basically, all you have to do is type in the FCC ID into this website, fcc.io, and it takes care of going through all of the government's website and finding the relevant information. And so if you type this in, if you were typing this exact link, you would see, oh, here's the schematics of the internal. You can see test internal photos, the user's manual, just a wealth of information about this. And what this gets you easily is the frequency that the device uses and the modulation, which are typically some of the harder things to understand about your device if you're just getting started with it. And that being said as well, that if you're used to standard tools like Nmap and Netcat that you would use for, say, technical work, on a network, that's the easy part, right? You can see the signals that get transmitted, and you get clear text, so you can run an Nmap command and interrogate a port. With wireless, you have to worry about getting a clean signal on the way in. That would be the same thing as if you were using Netcat or Nmap to say, hey, now I have to make sure that the pulses coming from my Ethernet adapter are coming in correctly and I'm getting a good signal. And so this is the first step of that, is just being able to see the frequency and the modulation. We'll talk a little bit about what modulation is going here forward. So you can do it the hard way. So if you had, program, I think this is SDR Sharp on Windows. In SDR Sharp, what you can do is basically just see, hey, here's a waterfall graph which displays incoming signals that on the radio spectrum that it can see. And you can just look at the raw blips. You can see, hey, the one to the far right is a lot wider bandwidth of a signal. You can try and basically divine the type of modulation from there, but trying to tease out the modulation, trying to tease out the frequency, is typically a lot harder and takes a lot more time that you could completely sidestep just by reviewing the FCC website. And again, any electronics sold in the United States, if it's legal anyways, should include the FCC ID. So again, I definitely swiped that image, I believe, off of Wikipedia because it's a pretty nice looking GIF. So when I say modulation, there's a bunch of different ways that that radio waves can transmit data. So if you think of a radio wave on the electromagnetic spectrum, it's basically like ripples in a pond, and there are a bunch of different ways that manufacturers and scientists, engineers have come up with to transmit data. Two main ones that you might see are amplitude modulation and frequency modulation. And this is basically AM, FM in your car. Amplitude modulation, you can see they vary the amplitude of the wave as it is received or transmitted. And that's how you can transmit data, is by basically saying, hey, high amplitude might be a 1, low amplitude might be a 0. And then frequency modulation, on the other hand, is you're modulating the wave as it goes in. So you might have waves that are far apart and then get kind of compressed like a spring. And those are different ways that the actual electromagnetic wave is modified, modulated to transmit data. An easy way to kind of see this is for something called on-off keying, where basically, if you had a high amplitude, that might indicate a 1 or 0, or it might indicate, or as far as like frequency modulation, same thing. It's just a way that you're going to transmit data. And you'll see this on-off keying or OOK in a bunch of cheap electronics. And so we'll kind of go through what you can do with that. So hopefully this makes sense so far. I'm trying to distill this down into its easiest and quickest elements to understand. So before, in the old days, you could use an audio editing program like Audacity to basically take a signal that was recorded from your software-defined radio and try and analyze the on-off signals. So again, this is the program Audacity is normally just an audio editor, but you can use it to analyze your signals. Luckily, it's gotten a lot better than this going forward. One of my favorite tools to use in recent years is called Universal Radio Hacker. I recommend just Googling it, watching a couple YouTube videos, but basically it does everything. You can run through a bunch of different modulation types. You can see the signal. You can zoom in, zoom out. You can record. You can replay. You can do a ton of different stuff with this, and it is workable with pretty much every software-defined radio on the market. It really is just like hitting an easy button. Somebody's done I wish I could give credit to it right now. I don't remember who the author of the tool is. As far as more, sorry, Altspace VR keeps unmuting me when I get out of it. As far as more tools and resources, there's HackerF tools, easy git clone install, Universal Radio Hacker, GQRX, SDR Sharp if you want to analyze stuff in Windows. RFCAT is a great tool if you have the Yardstick 1. OOK tools, if you know that your device specifically is using on-off keying, this will basically do everything under the sun. And then GNU Radio. GNU Radio, you could do a full talk in and of itself. There's even like a full GNU Radio conference that you can go to. That I'm definitely not going to dig into that because again, you could do full-on talks just about what that tool can do. So just a quick example, just again to show you how easy this is. If you have, say, the device from before that I identified, which was a little motion alarm, I knew from the FCC documentation that it's running at a frequency of 433 megahertz, which you can see is this -F. The -F indicates frequency, and I'm using the -R command to record this just to a raw file, and I'm using the HackRF suite just git clone and installed. And so this command, all this is going to do is record on that frequency on 433.920, 433 megahertz. And then playing it back, I just run basically the same command, but instead of the -R flag for recording, I just do the -T flag to transmit it. And so this is how I can catch a signal and then play back the signal. And you'd probably think like, wow, Eric, there's no way that you could do this and that this works on sorry, it keeps muting me. You think that there'd be no way that this is just as simple as it is just catching a signal that gets sent and then replaying it. But I'll show you how easy it basically is. So this is that same motion alarm from before. So basically, all I did is I recorded a signal that came from it, and now I can just transmit it and make the receiving base station believe that the transmitter is actually sending. You can see I proved it by just removing the battery from the back of it. So let's see if this video works. So you can see the alarm is going off. However, the battery is removed. And so that is should be scary enough. If you, I mean, again, this is like a maybe $15 alarm that you could buy off the internet. So how big of a security risk is it? Maybe not a whole lot, but in the same fashion that you can replay that signal, you could also create noise on that same channel, which would then basically disable the alarm from going off. And so that's just one method. Another one too is you can use it to click on lights. So again, you can see that I recorded and just simply replaying these signals back. Right. And so I'll play it again. So you guys can hear the audio. But if not, you can see the little red lights clicking on that. All I'm doing is again replaying that signal over and over. If you want to get a little bit more serious about it, you could just wait for a car to drive by a gated community and record that signal and then replay it. So this is my yardstick one hooked up to a Raspberry Pi, which I cloned the signal to a security gate for a neighborhood that one of my family members lives in. And so that you're looking at real world applications to where potentially $100 worth of hardware could get you into some restricted locations. If you have a dog shock collar, same thing. You can just replay these signals, so you can see the controllers right there, and I can make it vibrate, right? But it doesn't take a mastermind to realize that you could also make it probably replicate other functions of that dog collar and reverse engineer it from there. Really, my point of this is not to say, oh man, everything is vulnerable, but just it's interesting to see what devices that you just buy off Amazon that have almost zero security associated with them, that nobody's really looked at. Because with something like a your typical off the shelf hardware or software implementation, it's something that somebody could load up in a browser, use Kali or some typical tools, and find vulnerabilities in it. Wireless, on the other hand, requires at least some little bit of hardware, but after that, the barrier to entry, the barrier to finding vulnerabilities and exploiting some of these things is really quite easy. And that's really what my whole talk is geared at, is just showing how accessible it is and how easy it is. So with that, are there any questions? I don't know if you guys can ask questions from there if I need to go somewhere else. Renton. Well, I can also hop out onto the lobby too if you guys want to go ask questions there. Yeah, hopefully, this makes sense as to why, why and how to get started and how to compare different hardware options.
And is there like, do we just like, can like raise a hand or just ask a question or what?
Yeah, sure.
So can you talk a little bit about some of you're showing like some of the recording and retransmission of signals. Can you talk a little bit about some of the security countermeasures that are put in place against those things, like rolling codes and things like that, or is that sort of
Yeah,
more for
absolutely.
advanced talk? So
I mean that. So my goal for this was to keep it simple, but yeah, no, I mean that's definitely a great jumping off point to some of the security measures. So your phone, or so your phone, gosh, your like your garage door. A lot of garage doors implement what's called rolling codes, which means you can't just simply replay the last code that was used. It'll use a different, seed, or a different, numeric sequence to generate a new code. That way, somebody can't just sit there and say, here's the on-off key, and go from there. There was an interesting attack done by Sammy Kamkar called a roll jam attack, where basically it was like a store and forward type of attack. And so that was one way to potentially defeat that. There's also different mechanisms for, if you've ever heard of like Zigbee or Z-Wave, other wireless protocols used in home automation. A lot of those will include they will encrypt the signal as it goes through, so they'll have like a shared key. However, what's interesting about I believe it's Zigbee. Actually, Z-Wave might do the same thing, but essentially the way that it works is that there's a pairing sequence when you go to add a new device to that, to your home network, and when you do that, that key is transmitted in clear text. And so if you're an attacker and you have basically some hardware device that is just listening there, you could potentially just see that key as some user adds something over the network. And when you have that, now you can talk to all of the devices in that network, and you can even act as a member of that network. And so that's one of those other ways that when you look at it, it's there are definitely more security measures, but it's kind of like playing a game of cat and mouse. Once there's some security measure, there's always going to be some weakness to it. And the really hard part about Wi-Fi is that, or Wi-Fi and just wireless in general, is that all communication has to be done. Could be observed by somebody else. And where that's a little bit different is that if you are, say, on a home wired network, you have to find some way to potentially man in the middle some traffic, or be able to sniff or snoop on that traffic. As far as wireless is concerned, there's no way to detect if somebody is listening to your traffic, and so you could have somebody potentially just sniffing your traffic, continuously, whether that's your Wi-Fi traffic and they have your PSK, your pre-shared key, or if you're using God forbid an open connection where there is no encryption, or if you're using some home automation device that uh, you know doesn't transmit keys safely. Those are all security concerns and security risks.
Do you think you're going to see less radio frequency devices with the expansion of 5G, and like more that's going to be basically internet or cloud connected controls?
Um, No, I don't know. I think you're going to see a lot more wireless out there. I mean, if you just look at like what Elon Musk is doing to Starlink, there's constellations now of satellites flying above us. I think that there's always an interest in removing wires from the equation wherever you can. So, I mean, you might see less of it in some arenas, but I think overall you're going to see only more wireless devices come on the market.